Okay, thank you very much for the invitation. It is always a pleasure to come to Lumini. I like being here for the math, for the nature, for everything. And actually, I remembered when I came here that it was the last Lumini conference I was at that this whole business started. So somehow it feels like maybe not coming full circle, but looping once more to prove new theorems. Okay, so I'll be talking about something called fine curve graphs. And it is joint work in varying constellations that I'll indicate with Jonathan Bowden, Katie Mann, who's here, Emmanuel Militon, who's here, and Richard Webb. And what is all of this about? Well, the basic question that lies at the heart of all of this is to study symmetries of surfaces. Right, so there's this typical story that I like to tell when I speak at conferences that are not as narrow and focused as this, of saying, oh, well, we look at a surface, which is a very basic low-dimensional manifold. Of course, we've learned that even the one-dimensional ones are actually really hard, but the two-dimensional ones are also really hard. And just like in the one-dimensional case, the manifold itself is not where the complexity comes from. All of us understand surfaces from algebraic topology 1. But if you try to understand their symmetries, then it gets really complicated. Then you're very quickly studying really complicated groups. So what do I mean by this? So more precisely, there are many different ways that I could interpret this. And so I could look at diffeomorphism groups of varying regularity. I could look at homeomorphism groups. Or, and this is what I want to very quickly talk about first, I could look at mapping class groups. So let me start with this. So what is a mapping class group? Oops. OK, good. So very quickly, let's take sigma as surface. I don't know. Let's do this first. Sigma G is supposed to be a surface of genus G. Usually, the genus is at least 2, but sometimes it won't be. I'll indicate this. And the mapping class group of a surface, this is simply all the orientation-preserving homeomorphisms, say, up to isotopy. And why do I want to start with this? I want to start with this because these days I think we can say with some confidence that this group is much better understood than any of the other alternatives here. And to give you one example, I want to quickly remind you of a classical theorem which is really nice, which is the Nielsen-Thurston classification. So the mapping class group is well understood. So for example, we have the following theorem, which I'll phrase in a way. So I guess that's the Nielsen-Thurston classification. And one way to phrase this would be the following. Suppose I have a homeomorphism of the surface. Then F is isotopic to one of the following. So the first would be a finite order homeomorphism. Or let me rephrase this thing as saying up to isotopy. So up to isotopy, F is a finite order homeomorphism or reducible, i.e., there exists disjoint simple closed curves alpha 1 up to alpha k which are preserved, so such that F preserves the set of these alpha I. Or, and I'm seeing that I already used the board very poorly, but bear with me for a second. So let's pull this up. Let's pull this. Ah, that's the second one. Okay, okay, okay. Good, good, good. Or 3, F is something called pseudo-Anosov. And if you've never seen this before, it's a bit hard to absorb this in 2 seconds. But here's one way of characterizing this property, i.e., there exist singular measured foliations F. Everything's called F now. So curly F plus and curly F minus, such that F preserves these foliation topologically and scales the measure. So let me try to indicate what these scenarios are on these other boards here. So the first is, of course, easy to understand. What's a finite order element? We can all do that. You just take the surface and you say, in this case, you rotate it by 1 click. Right? You have an order 3 rotation of the surface. We can all sort of understand this. What's the second case? What's the reducible case? Well, in the reducible case, what you could do is you could take your favorite 2 curves, don't do anything to those curves, and just act on the complement of this surface, right? And that gives you a homeomorphism of the whole surface. And why is it called reducible? Well, it's reducible because really when you want to understand this, you might as well cut your surface at these curves and find a surface of lower complexity. In this case, you would go from genus 3 to genus 1 with 4 boundary components. And you can just try to understand your homeomorphism there. This is very good for inductive arguments. And what's the last picture? Well, the last picture is that for the pseudo-Anosov, locally, you have a picture like this. So you have 2 foliations that are transverse to each other. So these are these Fs. And what does singular mean? Singular means that at most points the picture looks like this, but we're on a higher genus surface which doesn't have non-vanishing line fields. So at some points, instead, you have a picture like this, where you have sort of prong-type singularities. And what does your map do? Well, your map set-wise sends leaves of the blue guy to leaves of the blue guy and leaves of the red guy to leaves of the red guy. But dynamically, it does something very interesting. Dynamically, it stretches one of these foliations and it squeezes one of the others. Right? So it's this typical, I don't know, Markov picture. You sort of decompose your surface into rectangles. Each of them you squeeze in one direction, you stretch in the other until it covers itself again. And so if you think about it like this, you see that this is really where the complicated dynamics is happening. So if I look at this with a dynamicist's eye, this is really the complicated case. The other ones are sort of dynamically less interesting. OK, it's all very classical. Why is this great? Well, this is great because, first of all, if I'm in the case of the mapping class group, where in the beginning I said we understand this, this whole up to isotopy business is not worrying me. Right? I could rephrase this as every mapping class is finite order or reducible or pseudo-Anosov. But somehow, one of the reasons why this is such a cool result is because in many different guises where the mapping class group appears naturally, this trichotomy has some kind of meaning. So I guess that's sort of now a meta statement, but often, so let me phrase it like this. There are many other characterizations of this trichotomy. And since eventually today I will be wanting to talk about these curve graphs, let me give you one. So let me give you a very, very brief introduction into the curve graph. Again, just like with pseudo-anosovs, it's not so wild, but the first time you see it, it takes a bit of getting used to. Less than pseudo-anosovs somehow. So what's the curve graph? The curve graph for me is going to be a combinatorial gadget where the mapping class group acts on that captures the intersection patterns between simple closed curves and captures a surprising amount of information about this group. So what is it? Well, it's a graph, so I need to tell you what the vertices are and what the edges are. So the vertices so the curve graphs, I'm going to denote this by curly C of sigma. So the vertices correspond to isotopy classes of simple closed curves. And the edges correspond to disjoint representatives. Okay, so what does that mean? Everyone always draws a little picture of the curve graph. Everyone draws essentially the same picture of the curve graph. But let me try as well. So here's sigma, that's my surface. And now what can I do? I can draw any embedded S1 on my surface as long as it is simple, it's an embedded S1, and essential. So it should be a non-trivial element in pi 1. Right? So this alpha here, for example, is one of these guys. And on the side of the curve graph, not the surface, such a curve gives me a vertex. Right? So far, so good. Here's another curve, beta. That gives me another vertex. And evidently, these two are disjoint. And so there's an edge between them. Fair enough. Let me draw one more. Here's another curve, which I'm going to call delta. That's again essential, so it is a vertex. Delta and beta are clearly disjoint, so there's an edge here. What about delta and alpha? Well, delta and alpha seem to intersect in these 2 points, but that's only because I've drawn it that way. Right? So remember, everything is up to isotopy here because we're currently studying the mapping class group, so I might as well tighten this curve up and say, look at, say, if we want to be precise, look at this delta prime here and say, aha, actually, if I want to really be precise, I shouldn't write alpha. I should write the isotopy class defined by alpha, beta, and delta. And then we see that the isotopy class defined by delta and by delta prime are, of course, the same. And delta prime is disjoint from all the others that I've drawn. Let me draw one more. Here's a gamma, just so that you see that there's some curves where you actually don't have edges. Right? So this edge really isn't here because this intersection here is even an algebraically non-trivial intersection. So the algebraic intersection form evaluates to 1, so not an isotopy clearly can't get rid of this. OK, seems a bit silly at first. Why do you want to study this? Well, one thing that's obvious is that the mapping class group acts on this guy. So the mapping class group of sigma acts on this curve graph. That's clear. It acts on isotopy classes of curves. It clearly preserves disjointness because we're acting by homeomorphism. Less clear, and this is a theorem due to Mazur and Minsky, is that this graph is in any sense useful. Right, so if you look at this, one thing you immediately realize is that this is not a particularly pleasant graph. This graph is locally infinite. For example, look at all the vertices connected to alpha. That's all the curves that are disjoint from alpha. So any simple closed curve on this side of the surface will be a vertex that's joined to alpha. And so this is a locally infinite graph. And it's not at all clear why acting on such a non-proper object might be helpful for us. But what Mazur-Minsky prove is that this graph is actually very pleasant, at least from a geometric perspective. So they prove that this is Gromov hyperbolic. So what does that mean? Well, first of all, how is this a metric space? So it is a metric space in the usual way that I interpret a graph as a metric space. I simply make every edge have length 1 and then take the induced path metric. And what does Gromov hyperbolic mean? This means that triangles are thin. So what does triangles are thin mean? This means that if I take 3 points and I look at a geodesic triangle between the 3, there's a center that has distance less than some constant that doesn't depend on your triangle from all sides. So there's sort of a thin center of every triangle. And why is this good? This is good because now, once we have this, we have the machine of geometric group theory. And so this is not a conference on geometric group theory. So let me very quickly summarize this as saying that once you have a nice action of a group on a hyperbolic space, you feed it into the machine of geometric group theory, and you get a payoff. So these days, once you have an action on a hyperbolic space that is even proper in the weakest sense, which this is going to be, you can use this to conclude lots of nice things. Your group won't be hyperbolic, but you get lots of nice consequences, like quasimorphisms or subgroup structure results, and so on and so forth. OK. Now, here's one reason a space could be Gromov hyperbolic. The space could be finite diameter. If your whole space has diameter 10, then every triangle will have a center that's with distance 10 to every side, right? Because the whole space is empty. So for this to be useful, I'm implicitly trying to convince you here that this space isn't finite diameter. It's actually big. And to come back to this here, I actually want to make the point that we can interpret this Nielsen-Thurston classification in this language. So let me do that now. So for example, and this is also due to Meza and Minsky, a mapping class F is pseudo-Anosov if and only if F acts on this curve graph with positive translation length. And this is sometimes called hyperbolically. But in this business, too many things are called hyperbolic. The whole space is hyperbolic, and now an isometry of a hyperbolic space is called hyperbolic if this holds. So what does this mean? This means that if this is very simple. It just means that I'm looking at an orbit, so I'm looking at my favorite curve, and I'm hitting it with iterates of my map. So now I get a sequence of curves, and what I'm asking myself is, how fast does this escape? Right, so I'm applying my map n times, I'm dividing by n to get a linear escape rate, and positive translation length means that this limit is positive. Right, and so what's the point? The point here is that we have translated this interesting property of being dynamically interesting pseudo-Anosov, which sort of lives purely on the side of surface dynamics, into a coarse geometric property of how this homeomorphism acts on this weird little gadget that we've built. Right? And this is sort of a powerful trick, because now we can try to either use all the stuff we know about surface dynamics and pseudo-Anosovs to study the curve graph. For example, this shows that it has infinite diameter. Or we can try to use the geometry of the curve graph to construct objects that are then dynamically meaningful. Right? So for example, it's a very easy consequence. You could build free groups just consisting of pseudo-Anosov elements, because it's really easy to get free groups acting as hyperbolic elements on hyperbolic spaces by ping pong. Right? And I'll come back to this later if I have time, but this correspondence is somehow even better. So Pseudo-Anosov naturally has associated to it these foliations. And by Klarreich's theorem, these foliations correspond to sort of the convergence points at infinity if I keep iterating my point forward and backward. So there's really a dictionary between dynamics and coarse geometry. Okay, now the spirit of this conference is that we want to go bigger and look at big groups. So mapping class groups are too small for us. And big mapping class groups are still too small for me. I want to go directly to the really big guns, which are the homeomorphism and diffeomorphism groups. So I'm now asking myself, how good is this theorem? So how big of a deal is it that we could only do this up to isotopy? So how important is up to isotopy here? And of course, you'll immediately see that the answer is very important. So the answer is very for numerous reasons. But let me give you one reason why this is very important here in this story that will fit with what comes next. And this is the following. Let's recall that we have something called the Berman exact sequence. So what's the Berman exact sequence? It is a sequence that says, aha, let's take the mapping class group of a surface which I've punctured at a single point. So this is homeomorphisms of the punctured surface up to isotopy of the punctured surface. And what I can then do is I can fill the puncture back in and map to the mapping class group of the closed surface. If you don't like this, you can also think of this as just homeomorphisms fixing this point up to isotopies fixing this point, and then this is the forgetful map that just forgets that I fixed the point. And clearly, this is surjective, because if you give me any homeomorphism, I can always isotope it so that the point comes back to where it started. But the point of this sequence is that there's a very interesting kernel here, and it's exactly the fundamental group of the surface relative to this point. And this is what's called point pushing. So what's the idea? The idea is that I have my surface here, I have my point here, and now I have a loop in the fundamental group. And how do I build out of a loop on the surface? How do I build a mapping class here? Well, I put my finger on the marked point, and I can locally isotope to move this point along this loop. Right? I just locally isotope this so that the point moves along the loop. And once it's done, it's back to P, and I take the endpoint of this isotopy. Right? So this is how you associate a mapping class of the punctured surface to a loop in the fundamental. So it's clear that I have this map. It's not really entirely clear that it's well defined. It is not clear that it actually is the whole kernel, but that's true. That's what Berman proves. And another theorem due to Kra tells us, so let's give this map a name. Let's call this P for pushing. If gamma in the fundamental group is filling, then pushing along gamma, seen as a mapping class of the punctured surface, is Pseudo-Anosov. Right? So this should not be entirely surprising to you. If I take a loop that is filling, so it cuts the surface completely into trivial regions, and I keep on pushing along this loop, it seems like I'm mixing up the whole surface. And in fact, Kra tells us that this is the case. If you already believe the Nielsen-Thurston classification, it's easy to prove this. You won't be finite order because you keep pushing along this loop. You won't be reducible because this thing is filling, and so eventually it will interact with any curve and move it away and move it to something that intersects itself. So it has no chance than to be Pseudo-Anosov. What does this have to do with what I said before? Well, what this means is that a representative f of such a map lies in homeo 0 of the surface, but shows behavior like a pseudo-Anosov of a finite type surface. Right, so if you ask yourself, how far have we come with this little Nielsen-Thurston classification and our gadget which detects it, it seems at first that we haven't gotten very far at all, because I can never see things relative to these finite points that I might be fixing. Right, which isn't the problem if you do mapping class groups. After all, this is a different mapping class group from this, and it's just living in different things. But if you're caring about the surface homeomorphisms themselves, if I just hand you this f, you don't know if it is just a map of the closed surface or if it is secretly a map of a punctured surface yet. Okay, so the mission statement now is, can we maybe try to develop a theory like this curve graph which allows us to use coarse geometry and maybe these neat tools from geometric group theory, but which can somehow actually deal with homeomorphisms rather than mapping classes? And before we do this, I'm going to give the game away. The answer is yes, this works to some degree. No, everyone expected that anyway. But before we do this, I want to tell you about one other example that should maybe convince you that there's problems beyond this. This seems sort of understandable. We have all these mapping class groups relative to points. We can still describe them with mapping class group tools. We can find them in the homeomorphism groups. Maybe you don't see this as a big problem. Here's a different kind of example. So a different homeomorphism. And so what we're going to do is we're going to start with a minimal filling geodesic lamination lambda on your surface. So what's a minimal geodesic filling lamination? So i.e., it is a closed subset foliated by complete hyperbolic geodesics relative to some fixed hyperbolic metric, so this is the geodesic lamination part. What does minimal filling mean? Minimal filling means that if I cut this out, this is a union of simply connected regions. So it's a union of ideal polygons. Okay. So let me try to indicate this. No one draws a picture of this, really, for good reason. So this is kind of tricky to draw. Everyone tries, and it never is really convincing. So what's the idea? What's an ideal polygon? So an ideal polygon, for example, would be something like this. It's an ideal hyperbolic triangle with all three endpoints at infinity. And now what you're doing is you're embedding this on your surface. So how does this work? Well, the sort of fat part of the triangle, this middle part, will go somewhere. And then you have these cuspidal regions, and they will start wrapping around your surface. Just kind of tricky to draw. They get thin very fast. They keep following each other. I don't know, something like this. And now you can see why. So filling makes sense from this. Where does minimal come from? Minimal comes from the fact that once you do this, you're sort of forced, because you want to avoid yourself to be foliated by embedded geodesics. You're forced to sort of recur and go everywhere. Every half leaf will be dense in something like this automatically. If you've never seen this before, how to think about it would be you take one of these guys, which are maybe more convincing, and then you just straighten out all the leaves with respect to the hyperbolic metric. And this will get you something like this. And another good thing to remember is that a cross-section looks like a Cantor set. If I look at a little transversal to this guy on my surface, these cusps of my lamination will cut through this infinitely many times. Every time you cut through this, you remove a little segment, just like for a Cantor set. OK, so suppose, I hope you believe me that we have these. Now we do the following. So now consider a cusp. So consider one of these cusps. And I'm going to draw this in the upper half space model of the hyperbolic plane. So let's say we have this triangle again. Now this triangle looks like this guillotine shape. It has one of its ideal boundary points at infinity, and the other two somewhere on the real line. And this embeds on my surface. What I'm going to do now is I'm going to look at a little subrectangle like this. And I'm going to look at a further subrectangle like this. Okay? And what are we going to do? So here, my homeomorphism f pushes up by 1 Euclidean unit. Right? So you just, here the map is just, I guess I could just write z goes to z plus I. That's what I mean. And here, outside of the green region, f will be the identity. And what will you do on the green region? You just do a bump function and interpolate between the two. Okay? And since we're pushing up by 1 Euclidean unit, the further up I am, the less and less I push in the hyperbolic sense. This actually nicely goes to the surface and gives me a map from the surface to itself. Right? So this is a map. What kind of thing is this? This fixes this lamination set-wise. Of course it does. It only works on the complement. And it somehow point pushes into the cusp. That's what this guy does. So what kind of map is this? Right? It's a homeomorphism of my surface. I can hit it with the Nielsen-Thurston classification, and I can see that this is actually really boring, because of course, essentially by how we built this guy is just isotopic to the identity. So f is isotopic to the identity. And if you think about this for a bit more, you can actually see that even if, and it's, let me write this, it's a finite order mapping class, rel any fixed point set, any finite fixed point set, I guess. Right? So the point is, if you imagine having a couple of fixed points somewhere here, they have a definite height with respect to this. And so if I take a curve and I start iterating my map, if I iterate often enough, the curve only changes way above where all the fixed points are. So the isotopy class relative to these fixed points never changes. I can still sort of push this down. Can you repeat what you wrote? Yes. So let me write this actually. So thank you. Do keep me honest. And I know that my handwriting is really bad, and I never know where it is really bad. So if I have a point, if I have P, a finite set of fixed points, right? So what can I then do? Then I can look at F restricted to the complement of this fixed point set. And I look at this as a mapping class group element of the punctured surface. This is still not interesting. Right? It's not necessarily trivial, because maybe one of my fixed points is sort of here, and then if I look at this curve, oh, sorry. No, if I actually do it, yeah. If I write this, then it's actually always just the identity, because the thing is away from this. So let me write. It's still trivial. So the fixed points are only away from this region where I do anything. So even on the punctured surface relative to the fixed point set, it is just supported on a disk, so nothing happens. OK, so I've spent a long time building an example that seems utterly uninteresting. Why did I do that? Well, now imagine what happens if I take a curve and just start iterating my map. And I've run out of space at the most inopportune time. So let me clean the board, while at the same time you think about what happens if I iterate the map. Well, I can talk, I guess. So right, imagine your map. Imagine a curve. The lamination is minimal, so the cusp will intersect the curve eventually. So there will be a little arc of my curve going straight across this thing. And then, as I keep iterating this map, this curve will be dragged into the cusp. And if you believe that somehow the, if you believe, oh, is it just this one? There's no one? OK, good. Yeah. Yes, this is, my cultural heritage has become apparent by wishing for wet wipes. OK. Right. So, but iterates f to the n alpha for any alpha seem to follow lambda. Right? If I don't think about mapping classes or anything, but just intuitively say, I have my cusp here, and I have alpha. Alpha will cross through this because it's a curve and this is minimal. What will happen if I iterate my map? Well, as I iterate my map, it will interact with this region where I'm pushing. And so if I take an enormous power of this thing, it will start to look like this. So this is f to the n alpha. And if I squint a bit, if I make n big enough, this thing will fellow travel the lamination really nicely. And this seems like there's something going on here that somehow mapping classes relative to finite fixed point sets can't see. OK. This took way longer than expected. But let me now tell you how all of this fits into a somewhat coherent picture. So now, instead, let's look at the fine curve graph. So what's the fine curve graph? I'm sorry for everyone taking notes. I'll do the fine curve graph by board magic. So I'll just amend this. What do we want to do? Well, the fine curve graph is just something where I want to not keep track of isotopy classes. So let's be bold and just do the obvious thing and remove the mention of isotopy classes from this definition. So instead of isotopy classes of curves as my vertices, I now take actual simple closed curves up to as my vertices, and instead of edges for disjoint representatives, I just want to actually have disjointness. Yes?
What's your notation for the fine curve graph? Is that a plus or an F?
It's a backslash dagger.
OK.
Ask me afterwards. Right. So what happens in this little picture? Well, the obvious thing that happens in this little picture is that now you see that this delta prime and this delta, they're isotopic, but I don't care about this anymore. So now, in this new finer curve graph, delta and delta prime will be different vertices. And delta prime themselves will be are disjoint from each other. So there's an edge here. Delta prime is disjoint from alpha and from beta. Delta is disjoint from beta. But delta prime isn't. But delta isn't disjoint from alpha on the nose. So this edge really isn't here. So this is why I call this the fine curve graph, because you're sort of refining your usual curve graph. One way of thinking about this is you take the vertices which correspond to isotopy classes and you're blowing them up into subgraphs corresponding to all the different representatives of your isotopy classes, and then you're reconnecting in a way that recognizes disjointness. Okay, well, the original guy was already not proper. It was locally infinite. This is, of course, worse. This is locally uncountable, but who cares? Now we have the advantage that the full homeomorphism group of the surface will act on this thing, and even the isotopically trivial guys now have a chance to do something interesting. And why is it any good? Well, this is the thing that I proved together with Jonathan Bowden and Richard Webb. And this is that this graph is still Gromov hyperbolic. So even though it is incredibly big and incredibly non-proper, at least the geometry is still somewhat useful. And this little advertisement here remains true. Here, let me maybe say, one consequence of this is that you can show that the fragmentation norm on Homeo 0, the conjugation invariant fragmentation norm, where you use everything supported on any disk, that this is actually unbounded. And the way you do this is that you build unbounded quasimorphisms that are still unbounded on Homeo 0, and this comes out of this geometric group theory machine. So this comes via work of Besvina Fujiwara, who really pushed this idea that even if you have a very non-proper action on a hyperbolic space, if you have even the most minute amount of regularity with respect to some axes, hyperbolicity is strong enough to get you quasimorphisms. So then you can use this to show that you have elements of positive stable commutator length, and from there you get that the fragmentation norm is also unbounded. Okay, but that's sort of so this is the stuff that happened last time I was in Lumini. So let me tell you about the new things and try to sort of shoehorn us back to this example here. So let's try to understand what we've seen in terms of trivial or non-trivial mapping classes and try to view them from the perspective of this graph. So so let me write Nielsen-Thurston question mark. So one thing you can do is, yeah, do you have a question?
Yeah, just to be sure, you're still requiring the curves to be essential in the fine curve?
Yes, absolutely. This is important. If you don't require the curves to be essential, then for any two other curves, there will be a tiny little circle that's disjoint from both, and then the whole thing would collapse to have diameter 2. So from a geometric perspective, you need this assumption. In particular, for this definition to work, you also want the genus to be at least 2. So you actually have edges. On a torus, this all still sort of works, but you need to allow slightly more general edges. For example, at most one intersection would work. But we'll actually hear about the correct or better definition later this week. And on spheres, you can't really make this work. You can make this work on punctured spheres, and we can do that. But on non-punctured spheres, there's sort of no baseline essential curves to start the whole procedure. OK, so what's the point about Nielsen-Thurston now? So remember, my perspective on the Nielsen-Thurston result was that for the curve graph, you could characterize being pseudo-Anosov by having positive translation length. That's on the board hidden now. So actually, we can try to play a game like this here. So here's a little construction. So if P in your surface is a finite set, then there's a 1 Lipschitz projection from the fine curve graph of your surface to the surviving curve graph, and ignore this if you hear this for the first time, of the punctured surface. So think of this as a normal curve graph. So technically what we're looking at here is the surviving curve graph. So this is a one Lipschitz projection which is natural with respect to the action of homeo sigma g minus p. So what do I mean by this? I mean, if I have a homeomorphism that fixes p, then it's equivariant. So then I could either act on my curve here and then project it, or I can first project and then act with the mapping class on the induced surface. And what this simply is, this is essentially the map which sends alpha to its isotopy class. Right? And this doesn't quite make sense if alpha goes through p, but if it goes through p, you just nudge it to one side a little bit, and you get a well-defined isotopy class of a curve here. Well, you get two. You can nudge to the left or to the right, but for a coarse geometer, none of this matters if I have a set of diameter 2. And it's one Lipschitz, because if two things have distance 1 here, they're disjoint, then their images will clearly be disjoint. Right? They can't go through the same point, so the nudging doesn't matter. If I nudge one, I don't nudge the other one, so I can't actually generate intersections like this. And as a consequence of this, you get that if f is a homeomorphism of your surface, f from p is p, and f restricted to the complement is pseudo-Anosov, and I now mean this in the mapping class group of the punctured surface, then f acts on this fine curve graph with positive translation length. Why? Because you look at an orbit, you look at what happens, it's a fixed point set, so I have this orbit here, I just push it into this gadget, now I have the Mason-Minsky theory that tells me that if I'm a pseudo-Anosov, I must make linear progress here, and because the map is one Lipschitz, I make at least as much progress here. And in a sense, this takes care of these Kra examples here. So we see that these homeomorphisms that are point-pushing maps and that are isotopic to the identity on the surface, but in their respective mapping class groups are doing something interesting, they now just fit into this story. They just appear normally as hyperbolic isometries of this fine curve graph. Nothing goes wrong. No. OK. Let me quickly mention one thing, which is that in certain scenarios, you can actually go backwards as well. So what about a converse? So this is a theorem now with everyone. So this is Jonathan Bowden and myself and Katie and Emmanuel and Richard, that for sigma 1, so the torus, we have that a homeomorphism of the torus that is isotopic to the identity has translation length bigger than 0 on this fine curve graph exactly if there exists a p finite that is invariant under this thing and the corresponding relative mapping class is pseudo-Anosov. So this, in a sense, is a hyperbolic Nielsen-Thurston in the case of the torus. It again says that a purely coarse geometric property of an automorphism of this graph completely corresponds to something that works. Why does this only work for the torus, and how does it actually work? I don't have time to explain this, but I think we'll hear about this on Friday. This is actually also equivalent to the fact that the rotation set of this torus homeomorphism has non-trivial interior. And this is sort of using this language, and the tools available in the surface dynamics of a torus is sort of instrumental to this whole story here. Do I believe that this is necessary? Well, I'm on record here, so I'm not going to say anything. But let me say it is a very natural question if this is true also for sigma g. And let me say I don't see any sort of obstructions to why this should be true. And why this shouldn't be true. Don't see obstructions for why this should be true. Fair enough. OK, good. So this is one thing one can do. This is sort of a little converse to this theorem. But to really test if we have a chance to capture the complexity of real homeomorphism groups, let's try to understand an example, or let's try to analyze. Yeah?
By this you mean equivalence of 1 and 2, right?
Sorry?
By this you mean equivalence of 1 and 2, right? Not the third one is not.
Yes, 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 yes. So right. Yes, so the equivalence between 1 and 2 should be true, yet now I've said it. I believe the equivalence between 1 and 2 is probably true in higher genus as well. But the problem is that we don't have a theory of rotation sets, or at least I'm not aware of a theory of rotation sets in higher genus which can do what we want it to do. That's sort of the problem. Right? You want to find fixed points and understand the dynamics relative to these fixed points. That's sort of a, there's some actual content here that uses, I mean, this uses not easy theorems in torus surface dynamics. OK, so what about this example? So what about the F? From the left board. So this acts on this fine curve graph, and we can now try to understand what kind of action is it. How does it actually act? So how does F act on the fine curve graph of this thing? And there's two comments I want to make here. So one is that F is the C0 limit of homeomorphisms supported on disks. Right? So this is clear. I just do this pushing motion, but I don't go all the way into the cusp, and also use the bump to do the cutoff at some finite height. And as I let this height go to infinity, this converges to my thing. And together with everyone, we prove that the translation length function is contiguous. So because you're supported on a disk, if you're supported on a disk, you will fix some essential closed curve, because there will be a essential closed curve disjoint from this disk. And so your translation length will be 0, because for the translation length, it doesn't matter which curve I take. So I just iterate something that doesn't move. So those together tell us that the translation length of F is actually 0. So I don't make linear progress. And that's kind of reassuring, in a sense, because we already know that somehow we couldn't see linear progress in any of these finite approximations. But have we gained anything? Does this complex actually tell us that this map is doing something interesting? And in fact, it is, because it is also true that orbits of this map have finite diameter, have infinite diameter. Yes. So what this means is that we see a phenomenon that's not available in the finite curve graph setting. You're sort of jumping to the punchline. Yes. Right, so for a general Gromov hyperbolic space, you have a similar characterization of isometries, just like in the hyperbolic plane. You're either elliptic and you have some finite diameter orbit, so you're sort of having, you're rotating along something, or your translation length is positive and you're translating along an axis, or you're of a third type called parabolic, where you fix exactly one point at infinity and you're pushing sort of along horocycles, making sublinear progress. And that's exactly what's happening here. The orbit of this curve has infinite diameter, but the progress it makes in the curve graph is sublinear.
Did you say that it has a fixed point?
Sorry?
Didn't you say that it fixes a point?
It fixes a point at infinity. So a Gromov hyperbolic space always has a boundary at infinity, and this will fix something at infinity.
Sorry, the guy supported on disks fix actually a point.
Yes, so the guy supported on a disk, this actually fixes a vertex of the graph. And that brings this actually as a fixed point. This guy won't have real fixed points, but it'll have a fixed point at infinity in the Gromov boundary. And so let me very quickly tell you why this is true. This is a trick that goes back to Hempel. And this is the following trick. I mean, Hempel didn't do this in this setting because he didn't care about the fine curve graph, but he cared about this for the normal curve graph, and his trick just works exactly the same. And the trick is that if the distance from alpha to beta in the fine curve graph is at most n, then there exists a cover of my surface of degree at most 2 to the n, such that alpha and beta have disjoint lifts. And why is this true? Well, this is true because if I think about the local picture, if I think about 3 adjacent curves in the curve graph, so I have some curve alpha here, and then I have a curve beta here that's disjoint, and there's an edge between them, and then I have a curve gamma that's supposed to be disjoint from beta, but not necessarily from alpha, so it's really complicated on this side. Then what I can do is I can take an order 2 cover, which unwraps at beta, and I can lift one of the curves to the left, and I can lift the other curves to the right. So at the price at moving everything up into a degree 2 cover, I can replace a segment of length 3 by a segment of length 2. Right? And this iterates. So this shows that this is true. And why does this help us here? This helps us here because if I go to a finite cover, this minimal filling lamination will lift to a minimal filling lamination of the cover. So the lift of your homeomorphism just pushes into the cusp of a more complicated lamination. But it stays filling. And so it'll have to intersect every curve. So this shows. And there's only finitely many covers of a given degree, so you can do it. OK, so what I've shown you now is actually what I've claimed in my abstract, namely that in this fine setting, something happens that we didn't see yet in the classical curve graph setting. There's homeomorphisms acting parabolically. Now, I want to end on an optimistic note in the sense of not all hope is lost. Namely, we sort of still see what the limit point at infinity should be. Right? This guy fixes this geodesic lamination. This should be the limit point at infinity. And work in progress with Jonathan and Richard, we actually show that geodesic laminations on the surface or geodesic laminations on punctured versions do give you boundary points in the Gromov boundary. Convergence means what you want it to mean in a Klarreich sense, and this actually is this thing. But I also want to be honest, so I should tell you that there's examples that are much worse than this, where they're parabolic, but the fixed points are much more mysterious. So come talk to me at any point during the week, and I'll tell you about weird homeomorphisms. And thank you very much for your attention.